Then we'll move on to the next talk. And the next talk will be a bit of a challenge for me. I'll show the video, and I hope this works because I have it embedded in Firefox, and I hope this will also transmit everything that needs transmission. So I hope you can see the video now, and I'll just start it, hoping it will.
Yeah, Katinka, actually, I'm here if you want, but I think maybe the video, how many minutes do we have in the video?
It has 18 minutes.
18. Yeah, so I think, yeah, it would...
You want to give your presentation yourself?
I think, yeah, I'm debating whether if I give a presentation, I think it might take even longer than 18 minutes. I can try to give the presentation.
As you like, as you like.
Okay, so yeah. Okay.
Does the video work for everyone? Can people hear it?
I wasn't hearing, but we can try. Let's try one more time the video then.
Excuse me?
Yeah, I wasn't hearing the video, but let's try maybe one more time the video then. If it doesn't work, then I present.
Okay, so if you cannot hear it, then you have to give me feedback.
Yeah.
Or I have to.
I cannot hear it.
You cannot hear it. Okay, maybe then you try, and I have to think a little bit how I would get the.
Yeah. So
the sound source is wrong, I guess.
Okay.
But if you can just take over, that would make it easier at this moment.
Yes. Okay. So let me share my screen. Do you see my screen?
Yes.
Yeah. So I will make a very brief presentation, and then this will allow us to have more time for questions, okay?
Yeah,
so hi everyone. So my name is Daniel, and I'm going to present this work on blockchain privacy through merge avoidance and mixing services. This is joint work with Jefferson, Eduardo, and Carlos. And our work is motivated in part by privacy issues in next generation crypto systems such as Monero, which try to push the levels of privacy to push privacy to higher levels, right? And here is the outline of the talk. I first introduce the problem, then talk about the two main points that we discussed in our work, which are merge avoidance and mixing service, and then conclude. So we have kind of first generation crypto systems such as Bitcoin and Ethereum, and next generation like Monero and Zcash. And these first generation systems, they are good for authorities in the sense that it's easy to track malicious behavior. But these next generation systems, they, as I mentioned, push the privacy level to higher degrees. And now the question is, how can we add additional strategies to increase the privacy of these more traditional systems such as Bitcoin and Ethereum? And in this talk, we are going to discuss two ways in which people try to do some linkage in financial systems that we want to avoid in Bitcoin and Ethereum. So we can link between wallets from the same user, or we can link between users to shared coins. So the first corresponds to determining that two virtual wallets are from the same user. So, for instance, if two virtual wallets are owned by a coffee shop, and we learn that they are used to pay the salaries, then eventually we may learn the values of the salaries, for instance, of the employees. And the solution to this is to do what we call merge avoidance, which is to avoid multiple input wallets sending coins to the same output address. The second kind of linkage is different in the sense that it doesn't refer to the same user, it refers to multiple users. So we want to avoid linkage across multiple users, but through a given coin. So we have a single coin, and the attacker wants to determine the path that this coin traversed through the network. And to avoid that, to protect against this linkage, one solution is to use mixing services, which mix and the path that the coin traversed by adding relays to this network. So the strategies to increase are then merge avoidance and mixing services. The goal is always to obfuscate the network. The first relies on the sender and receiver, and the second, the mixing service, relies on the network of users. And what we are going to show is that one sort of merge avoidance is NP-hard, and that one sort of mixing services is impossible to be executed if we want to be incentive compatible both for senders and relays. So let's start with the merge avoidance, showing that it's NP-hard. So there's prior work, of course, on merge avoidance, which was proposed in 2013. And then there were related works as CoinJoin, and there's even a tool called BitTODIN that tries to do this linkage between different walls being owned by the same user. It tries to automatically detect that two walls are from the same user. And from the theoretical point of view, there is a long-lasting history of these coin exchange problems, which are sometimes referred to as Frobenius coin exchange problem. And our contribution here is to relate these fields, theory and practice, by showing that these coin exchange problems may have implications to privacy in blockchain systems. So here's our goal, is to transform, given a transaction graph, to transform this graph in a new graph where we don't have these merges that you see here in the slide, right? So as we see, we have multiple input addresses merging together in a single transaction, and then we have these two outputs. But when we have these multiple inputs merging into a single transaction, this is a strong evidence that these input addresses are from the same user. And that's what we want to avoid, this linkage of input addresses. So here the solution is kind of trivial. In this example, we just break this transaction in 3 transactions, and now we don't have the merge anymore, right? But the challenge is to determine the minimum amount of transactions, because as we saw in the previous talk, there is a fee associated to each transaction. So what's the minimum number of transactions that we can have to avoid this merge while still doing this in a robust way, right? So here is our first theorem. We say that multi-target merge avoidance is NP-hard. And reduction comes from the partition problem. If you have a set of integers, then to partition these integers in 2 groups, where the 2 groups have the same total value, is known to be an NP-hard problem. So, of course, multi-target merge avoidance is also NP-hard under this formulation. What is also interesting is that if we do some subtle changes into the problem, such as, for instance, assuming that we have instead of having multiple targets, we have a single target, and that the second output of the transaction is just an exchange, just a change. It should be change and not exchange. Then we have the single target merge avoidance problem, and in that case, the problem is actually solvable by a greedy polynomial algorithm, because we only need to rank the inputs, select the topmost inputs that meet the target, and then transfer these to the output, and the change value can be an arbitrary value. So this concludes the first part of the talk. If there is any question, maybe let's move on to the second part. So incentive compatible mixing is impossible. So this is now referring to the case where we have a source and a target. And now what we want to avoid is not the merge anymore, it's the linkage. So we want to avoid that users are able to track the paths that a given coin, like if we think about a physical coin, we can't track its history. If I give you the coin, you can't tell where it passed through, but in this crypto system, sometimes this is possible, right? And we want to avoid this kind of linkage. And to avoid that, one solution is to add additional relays in this transferring process, right? So the question is, can participants take advantage of this? So is it possible to do this in a robust way? So one way to increase the robustness, to increase the privacy, would be to add additional relays to the network. This is what mixing services do. They, like Tor, they add additional nodes to the system. And here we consider a zero-sum credit system where the source pays an amount to have this service, and this amount is divided between the relays, right? So that participated to help the source to have its credits transferred in a private way. So we call an edge insertion attack an attack where the relays, they perform a civil attack where they claim that actually there are 2 or 3 relays, and in reality they are just a single relay. And the question is, can we avoid this kind of attacks, right? So the impossibility result says that under the following assumptions, there is no zero-sum credit-based identity concealment process to prevent simultaneously edge insertion attacks performed by the applicant and by the concealment nodes. So the 2 main assumptions are that the credits paid are lens dependent. So the credits that you pay to use the service should only depend on the length of the path, and also uniformity, meaning that all the nodes involved in the process should receive the same amount. So the total amount is equally divided by the relay nodes. So what we show is that it's impossible, and the intuition is that it's impossible to be compatible both with the sender and the relays. Why? Because for the concealment nodes, right, for the relays, the reward will need to be decreasing with respect to attack level. But for the applicant node, for the sender, it would need to be non-decreasing. So as it's impossible to be at the same time decreasing and non-decreasing, we have this impossibility result. Here we have some possible ways to circumvent this impossibility result. But actually, this final discussion here also talks about about the applicability of this impossibility result. And actually, it turns out that in many systems, we have source routing, meaning that when the sender decides to use this mixing service, like in Tor, for instance, it may already set the path beforehand. So if that's the case, then if one chooses a route ahead of time, then deviations would result in a route not being able to decrypt the message. So that's in practice one of the ways to circumvent this impossibility result, because one of our fundamental assumptions in this impossibility result is that both kinds of civil attacks, both from the sender and the relays, are feasible, and sometimes they are not. So thanks for your attention. And
Thank you very much. Any questions? Anyone wants to ask something? Nobody? Then shall we just move on to the